So let's write down the main quest. Main quest is to prove that Fourier series converge in L2. That's how you would say it. Fourier series converge in L2. Yeah, when the class was double booked on Tuesday, there's some engineering class where they were giving presentations, and they're like, oh, what class is this? I was like, it's advanced analysis. We're about to prove that Fourier series converge in L2. That's what I told them. I was very proud. If you're an engineer, you'll know what Fourier series are. You don't worry about the converge in L2. You just say, oh, whatever they do, what we need to do. But this is what we're doing. And so what does this mean? It means if you take some function f, and you write f as you write it as an infinite sum of sines and cosines. So you do the sum of n equals 1 to infinity of the inner product with f with the function sine of nx and times the function sine of nx plus the infinite sum from n equals 1 to infinity of the inner product of f with the function cosine of nx times the cosine of nx. So this is a linear combination of sines and cosines. And I've only forgotten one piece. Can anyone tell me which piece I forgot? I've forgotten two pieces. I've forgotten at least two pieces. What are the things? Yeah.
I need a constant up front.
You need a constant, right? So I have sine of nx from n going from 1 to infinity. I have cosine of nx from n going from 1 to infinity. You also need the function 1. So you can also do plus the inner product with f with 1, which is also known as the average value of f times 1. So this sort of is adding on the average value of f. There's one other thing I forgot in these formulas. It's the thing that is constantly forgotten over and over again by everybody all the time. Yeah.
It's the 1 over.
The 1 over something. Exactly. Yes.
Something with a pi.
Something with a pi. Does anyone remember what it is? That's exactly right. Yeah.
1 over square root of pi for sine and cos.
That's right. So you got to divide by square root of pi for sine and cos. And then for the function 1, you don't divide by square root of pi. You divide by square root of 2 pi. And that makes the functions normalized. So without the pi's, they are orthogonal. But with the pi's, they are orthonormal. So the function sine of nx, its L2 norm is square root of pi. So if we divide it by square root of pi, now its L2 norm is 1. And now essentially you should think of this as if you're working with vectors in R2, you're working with unit vectors, vectors that are length 1, and then they add together nicely in the way that you would think. And our main quest is to prove that these things are equal. And by equal, we mean in L2, right? So as functions in L2, thinking of this as a vector in L2, and thinking of this as a limit of vectors in L2, right? You have infinite sums are actually limits, and we know what the limit in a space like L2 means. We want to prove that f equals those things. Okay, that's our goal. And what do we have so far? We ended last class with this amazing inequality called Bessel's inequality, or Bessel's equality and inequality. And this was the very last thing we did on last class. And it says that if you do the difference between the thing on the left and the thing we want on the right, it's something. And I think this is the way it was stated in the textbook. And it was a finite sum in the textbook, k equals 1 to n. So Bessel's equality, this is a finite. This is for finite orthogonal sequences. Let's say orthogonal. Let's do orthonormal. I think that makes the math easier. Orthonormal sequences, or the bookkeeping easier at least. Okay, you do the sum of xk times xk squared. So x1 ... to xn is a finite orthonormal sequence. ONS is an orthonormal sequence. And you look at x versus this expansion. And this is exactly what we're doing over here, right? So over here there are functions. So we called it f, but it's an element of the space L2, so you could call it x. And then we're comparing with a finite sum on the right-hand side. So what happens if you add up finitely many? How far away would you be, right? The norm squared tells you how far away you would be. And the theorem says that this equals, okay, let me get the actual statement of the theorem so I don't botch it. The theorem says this thing equals the norm of x squared minus the sum of k equals 1 to n, and then you do these inner products, xk squared. So this is where we ended up before, and the proof was basically by a Pythagoras theorem. And it was kind of a gnarly one. You had to make the right things appear. The way we did the proof in general is we replaced these coefficients with alpha, and we said if you replace it with alpha, there's an extra term here that depends on alpha. But if the alphas are exactly these inner products, then everything cancels, and you just get this nice equation with 2 terms instead of 3 terms. Okay, so that's where we left things off. And the reason this is such a nice thing to notice is this implies that the norm of x squared minus all this stuff is greater than 0, because norms are always greater than 0. So if this is the norm of something, it's greater than 0. And then we can move this something to the other side to get that the norm of x squared is greater than the sum from k equals 1 to n of xk. And the reason this one is so exciting is because the left-hand side is the upper bound, and it does not depend on n. And so if it's true for every n, then it's true in the limit. So that's because the right-hand side is getting bigger and bigger and bigger. So if it's true for every single one, it's also true in the limit. Then true as n goes to infinity 2. And so we have the norm of x squared is greater than or equal to the infinite sum from k equals 1 to infinity of xk. So now we have an infinite sequence. So for infinite orthonormal sequences, so now they're infinite, have this. And this one is called Bessel's inequality. And it's saying when you do this infinite sequence of things, it's going to be bounded above by the norm of x. And the reason that's exciting is that means it converges to something, right? This infinite sum must converge to something. It can't blow up to infinity because there's a lid on how high it could go. And the way you can interpret this is if you have a function, so you have x you can think of as an element in the Hilbert space or the vector space you're doing. Okay, let's do it with f to be a little bit more concrete. So let's say f, you have f in L2, and then on the other side, you have this sequence of inner products. You have f sine of 1x, f with sine of 2x, f with sine of 3x, and so on. Okay, that's a big list of numbers. I'll put commas so people know I'm doing a big list of numbers. I guess you also need the cosines, cosine of 1x, f cosine of 2x. So this is a giant list of numbers. It's an infinite list. Okay, and then don't forget everyone's favorite, the average value of f. Okay, and then put in the square root of pi's in the right place. Square root of 2 pi. Square root of pi, 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 square root of pi. Okay, so you have a function, and then on the other side you have a big sequence of numbers. And what this is kind of telling us is this big sequence of numbers is in lowercase L2, okay? This is in, so some sequence in lowercase L2. So we started with a function in capital L2, and by capital L2, maybe I should specify, I mean on the interval minus pi to pi. And then you can map it into this thing, which you can think of as an element. It's a big sequence of numbers, and it's in lowercase L2. The reason it's in lowercase L2 is sequences that are square summable. And this inequality proves that it's square summable. It's got to increase up to something, and therefore it's square summable. It has a finite infinite sum. So this is a map from capital L2 into lowercase L2. You can kind of think of this as a little bit like a fingerprint. Like a function in L2 is a crazy infinite dimensional thing, right? Like a function in capital L2 is some insane function. It could go up and down and up and down, and it could do like weird things. It could be discontinuous. As long as the integral squared is finite, it's some function. And this maps into a list of numbers. So it could be like, a third, a fifth, ... To give a concrete example, I opened up an old file from the very first day of class, which was this function. It was the function in green over here that is a little bit hard to see. It's the function which is 1 between negative pi over 2 and positive pi over 2. This function looks boring, but I assure you this function is crazy because it has discontinuities, okay? So it's some weirdo function. And then on the other hand, we saw that you could convert this function, you could think of it not just as its formula, but you can think of it in terms of just cosines. So it turns out all the sines integrate to 0. All the sine numbers are 0. So this function, when we map it into lowercase L2, it'll become the sequence of all zeros. And then you have this sequence with 2 over pi n, and sine of n pi over 2 is actually doing plus minus 1 stuff. So as you go around the circle, sine of n pi over 2 is sometimes 1, sometimes minus 1, and sometimes 0. So when we map it into the coefficients, we get something like this. Let me write that down. So example, the function f of x, which is the indicator function from minus pi over 2 to pi over 2. This gets mapped into the sequence of all zeros. So the signs are all 0, 0, 0, 0, 0, dot, dot, dot. The sign integrals are all 0. Okay, the average value of this function is a half. So the inner product of f with 1 was a half. So that's maybe the first number on that list. And all the cosine ones, the answer, it goes minus 1, 1. Wait, I guess it goes 0, 1, 0, minus 1, 0, 1, 0, minus 1. So the other list goes like this. And it starts with n pi over 2. So it starts at 1. So 1, 0, minus 1, 0, 1, 0, minus 1, 0, dot, dot, dot. And this was the inner product of f with the cosine of nx. And then I had to divide by n, right? So maybe this divided by 3. Okay. Maybe did I forget a pi or something? Let's go check the thing. It says there's a pi. Okay, let's put the pi back. Pi. Oh no, I've lost my pen. Okay, here it is. Pi. Okay. So in other words, we have come up with a way you can take a function and crunch it down into a sequence of numbers. Is this useful? You might say, hey, wait a second. Wasn't the first class also talking about how a function is just like a big, fancy vector is a big sequence of numbers? Like you could think of f of 0, f of 0.1, f of 0.2, f of 2 times e divided by 7, all the, just like think of all the possible x values, and then it's also a sequence of numbers. So you've taken a big collection of numbers and you've turned it into a big collection of numbers. Have we done anything useful? But why is that actually useful? Yeah?
The second one is countable?
Yes, very good. So the second one is countable, and this one is uncountable. So we've taken an uncountable number of things and we've crunched it down into a countable number of things. This is actually extremely powerful. The reason you can do that, this would not work for any function. It only works for functions in capital L2. So it turns out this is somehow saying that even though an arbitrary function is an uncountable collection of numbers, a function in capital L2 is nice enough that you can figure out what's going on with a countable number of numbers. So this is one thing, is that it is countable. And the other thing is that not only is it countable, but these things are sort of in order by usefulness. So for example, the 10th coefficient here, or the 7th coefficient, this is how much this thing is oscillating. It's the inner product with cosine of 7x, and cosine of 7x goes up and down and up and down and up and down very, very quickly. If I were to delete everything at 7 and further, then I would capture most of the behavior of the function just in the first 6 numbers. So we're capturing 100% of the behavior in some sense with infinitely many numbers, but the numbers are sorted sort of in order of importance, so that if you deleted some of them, you would still get pretty close. And that's exactly what is going on in Desmos, because of course, real-life computers can only do finitely many numbers. Let me put capital N equals 7 here, and here is the first 7 functions. So I've deleted anything in the green function that is oscillating faster than 7 times per interval, and I've kept only the things that are oscillating 6 times and slower, or maybe I've included 7. Okay, we're keeping 7, we're throwing 8 and higher out. And you can see we're most of the way there. We're most of the way to approximating this function. This idea is used in your computer all the time. This is how, for example, MP3s are stored. So MP3s, when you listen, a microphone will listen to sound like hundreds of thousands of times in a minute. So it'll sample at a rate of like 10,000 times per second or something. So if you were to write down a full song of what a microphone records, it would be like billions and billions of samples of, oh, the microphone moved up and then it moved down and then moved up and then moved down. And then it would take up like a terabyte on your computer. What they do in an MP3 is they first convert the millions of things. They think of that as the green function. They convert that to a sum of sines and cosines, and they say throw out all the sines and cosines that are higher than the frequencies humans can hear. Just throw those away. Keep only the red function. And then when you play back the red function to the human ear, it sounds the same as the green function. And so this greatly reduces the amount of storage you have to do. It's the same thing with JPEGs. They do the same thing, but in space, to record pictures. So this is a highly effective way to record data by using this correspondence, right? So take something which is extremely high dimensional, crunch it down to countable dimensions, and then you can even throw away all but finitely many, and it should be a pretty good approximation. So this is an extremely powerful idea. questions or comments about any of that? That's why we're doing this stuff. I think it's important to have the big picture. Otherwise, it seems like we're just doing crazy calculations for no reason. Okay, there is one thing that should bother you, is I've told you how to crunch the function down into here, but does it actually work the other way, right? So question, this is an open question we have not resolved yet. Question, does it work in reverse? Does it work in reverse? And this question of does it work in reverse is exactly what we're trying to prove. This was the idea we had before, right? So we take a function, we crunch it down to the coefficients, and then we ask the question, is the function equal to the function you would make out of the coefficients? So, and the answer will be yes for Fourier series. And when the answer is yes, we call that complete. So definition for orthonormal sequences where the answer is yes, so when it's possible to go both ways, you can both convert the function into an infinite sequence of numbers, but you can also convert back. If you're given an infinite sequence of numbers, you can convert it into a function, and they are inverses of each other. Then we call that thing complete. Okay, let me copy paste the definition from the textbook, so I get the number right. Okay, here we go. And I've drawn a big circle around it. Okay, here we go. Definition 3.4.12. So an orthonormal sequence is complete if every function x, or every element x, can be written as the infinite sum of x inner product xn with xn. Remember, the map that I gave you before was x gets converted to this infinite list. X, x1, x, x2, dot, dot, dot. So this is converting something from the inner product space into a sequence of numbers in L2. And then this equation over here, 3.30, is converting the sequence back into an element of the inner product space. And if that is equal to x, then both operations undo each other, and we say the whole thing is complete. Okay. So when this happens, the space is, people say, isomorphic to lowercase L2. So we have a map from E that maps into lowercase L2, and then we have a map back. The map into it is take the inner product with all the elements of the sequence, and the map back is to do this infinite sum. And if they undo each other and they're the same, then it's isomorphic. And the key part of this is that, so if we call this map T, so T goes from E into L2, then this is saying the inner product of Tx, Ty equals xy in L2. Wait, this one's in L2. This one's in E. Okay. Okay. This is kind of a little extra. This is sort of in the textbook, and we're not going to do it in detail. But what this is saying is when you have a complete orthonormal sequence, your space might as well be lowercase L2. So you can convert very complicated spaces. You can once you've identified this complete orthonormal basis, now they are both copies of L2 in practice. Okay. So that's what we're doing. So in this language, the thing we're trying to prove is that sines and cosines are complete. Sines and cosines. To do still. Sines plus cosines are complete. Okay, and the textbook, I think, has a number for this. The textbook number for this. Is there an example? Okay, here we go. Example. This is running forward a little bit. Example, 3.4.17. These functions are a complete orthonormal system. So they're complete and they're orthonormal. The textbook uses system instead of sequence sometimes. The orthogonality follows by this. So you can prove they're orthogonal by doing some trig identities. Those were the integration things I told you about earlier. Okay. Okay. And then there's a little bit more on the next page, which says, okay, here is the finish off of this trig identity, proving that the cosine squared and the sine squared are they are. Why is it complete? Completeness follows from the completeness of the previous example. The previous example is doing complex cosines and sines. So the previous example is doing this. And let me copy paste this over here because there is an important part I want to get to. 3.4.16. So this is basically sines and cosines mixed together. And this is a complete orthonormal system in capital L2. And this is the part that I want to highlight. The proof of completeness is not simple. That's going to be the next section. So we're going to prove this, but there's some sneaky tricks that you have to do this. So to prove that the sines and cosines are complete is quite tricky. It's pretty easy to see that the sines and cosines should be orthogonal, and this is what Mr. Fourier originally did. But then this was left for several hundred years until some people came back and did it. And we're going to do that probably on our last class next Thursday. Okay, so that's where we're going. We're going to need a couple more tools to prove these things, and we're going to learn a little bit more facts about complete orthonormal systems. This is a great place for questions or comments. Okay, so let's continue then learning more facts about orthogonal and orthonormal systems. And the next thing I want to prove to get all this stuff is when can you do an infinite sum of an orthonormal system? Okay, so this is theorem 3.4.10. And it says, if you have an orthonormal system, Xn is an orthonormal system, we don't know it's complete yet, then consider the sum like this. So we're going to do the sum of alpha n times Xn, where alpha n are scalars. Alpha n in R are scalars. So we often use this notation that X and like Latin letters are elements of the space, and alpha n are scalars. So we're doing alpha n times xn, and we're looking at this infinite sum, and we're going to ask the question, when does it converge? And it turns out there's a very satisfying answer as long as you're in a Hilbert space. So we're going to do is an orthonormal system in a Hilbert space. In a Hilbert space. And remember, a Hilbert space H means that it is complete. Don't get confused because this complete is different than the complete we just did. They're both called complete because mathematicians can't come up with any unique names. But this one, Hilbert space complete, means Cauchy sequences converge. Right? This was this one that we did all the way back in chapter 1. Cauchy sequences converge. That's what it means. Okay. So we're going to look at this infinite sum. And as long as Cauchy sequences converge, then this infinite sum, it converges if and only if the sequence alpha n is in lowercase L2. So this sum, it converges if and only if, and that is the sum of the alpha n squared is less than infinity. So in other words, you do alpha n as the coefficients, and it will converge in the space H if and only if these things converge as numbers when you sum them. So this is this idea of mapping this thing into lowercase L2, i.e. alpha n as a sequence is in lowercase L2. Okay, that's the theorem. The theorem's not super duper difficult because basically if you do the norm of this thing, you're going to get that by Pythagoras. So that's what's going to happen. And that's the theorem. Okay, let's prove it. So the proof, I guess, has two directions. And depending on how much you want to reuse our ideas from chapter 1, you can make a very short proof, which is what the textbook does, or you can do a medium length proof, which is what I'm going to do. So let's start with this way. So suppose the sum of the alpha n squareds are finite. So in other words, pretend you knew that the coefficients were in lowercase L2. Okay, then notice by Bessel's inequality. Then by Bessel's inequality, if you do the sum of n equals 1 to infinity, or let's do a finite number. Let's do the sum from k equals 1 to n. K equals 1 to n of x alpha k xk. And we take the norm squared. This will be the norm from k equals 1 to n of alpha k squared. And this will be equal to, this is also equal to this infinite sum, k equals 1 to n of the norm of alpha k xk squared. And this is not by Bessel, like I said, this is by Pythagoras. I named the wrong famous dead guy. Okay, by Pythagoras. Okay, so this is true for any n. And this number in the limit n goes to infinity is converging to some finite number. So now we take the limit as n goes to infinity. Take the limit as n goes to infinity. And what we conclude is that this infinite sum, k equals 1 to infinity, of the norm of alpha k xk squared equals this infinite sum of alpha k squared, which is less than infinity. Okay. And this means the sequence is absolutely summable. Therefore, this infinite sum, alpha k xk, is absolutely summable. Okay. Okay, and this is where you can be a little bit, you can do more work or you can do less work. If you want to say the fastest way possible is you can remember that in a complete space, every absolutely summable sequence is convergent. So this is some fact from chapter 1. In a complete space, every absolutely summable sequence is convergent. So if it is absolutely summable, like the sequence is here, then it converges to something. And so because we're in a complete space, since H is complete by this fact, therefore, the sum from k equals 1 to infinity of alpha k xk converges. This is the sort of medium length proof. If you want to do the full length proof, you would sort of prove this fact. And the way this fact works is you prove that the sequence summing up to n, so from k equals 1 to n of alpha k xk, you prove that that is a Cauchy sequence. And the reason it's a Cauchy sequence is because differences, this is like the long proof sketch. Long proof sketch is you let Sn be the sum from k equals 1 to n of alpha k xk. And then if you do Sm minus Sn, that will be the sum from k equals m plus 1 to n. Or maybe the reverse, maybe you start at n plus 1. Yeah, okay. And prove Sk is Cauchy. So if you do differences of the sequence, you get little pieces of this tail. And when the thing is absolutely summable, this thing will be Cauchy because you can make the tail smaller than epsilon. And then therefore you can make the distance between Sm and Sn less than epsilon. And that's why the Sns will be Cauchy. So this was the kind of exercise we had way back in chapter 1, and it's coming back now to haunt us, I guess, again, if you don't like Cauchy sequences. But that's what's important. Okay, so we use the completeness. And if you have something that is convergent in norm, then it's all going to work out. So there you go. That's the proof of one direction. Questions or comments about that one? Okay, let's see. Yeah.
So for this direction, we're able to drop the xk because they're orthonormal.
Where did the xk's go?
Yeah.
Yes, that's right. So the alpha k xk, because they're orthonormal, that is exactly norm 1. So it really should be alpha k squared times 1, which is the same. Yeah, that's right. So it's important they're orthonormal here. Otherwise, it's not a true statement. Very good. Yeah, and similarly, the norm squared of the thing, right? The reason this equals that is because they're orthogonal. That was Pythagoras. Okay, that's very nice. So yeah, the final thing, whatever it converges to, the norm of the thing it converges to will be this infinite sum. And we're going to see that more explicitly in a different proof. Okay. The reverse direction is also not so bad. So the other way. So suppose the sum, the sum from k equals 1 to infinity of alpha k xk converges in H. So this infinite sum is converging to some element in H. Therefore, let's call that thing x. Let x equal the limit as n goes to infinity of the sum from k equals 1 to infinity of alpha k xk. Oh, okay, k equals 1 to n. Okay, and then we know x minus this thing, k equals 1 to n of alpha k xk. This limit is 0. That's what it means to converge in norm, right? So this is all in H. Means the norms are going to 0. But this thing we had a formula for. That was the Bessel equality. So this is the limit as n goes to infinity. It's the norm of x minus the sum from k equals 1 to n of the norm of those things. And in that case, it's alpha k squared. Alpha k squared equals 0. This is by Bessel equality, if you want. I guess you could do it directly by Pythagoras. Maybe that's just Pythagoras again. Well, however you want to do it. By Bessel's equality with alpha k is the inner product of x with xk. Okay. And this thing is saying that the norm of x equals, just by rearranging the limit from k equals 1 to n of alpha k, which is the infinite sum. Okay, so in other words, the infinite sum exists, and it does not only exist, it is equal to the norm squared. I forgot the squared here. And let's put squareds everywhere, so it is actually a true statement. Okay. Okay, and so therefore, alpha k is in L2, and not only that, the infinite sum is equal to the norm of this element x squared. Okay. All right. Okay, so that tells you both ways. And this kind of tool is used to prove things about completeness. We're gonna see that in a second. This is gonna lead us into something called Parseval's equality, which is like Bessel's inequality, but is an equality only. Questions or comments about this one? Okay, let's see this one coming up. I think this is the next thing. Okay, I think even before that, we have this theorem right before Parseval's identity that is essentially one of the most useful ways to prove something is complete. So an orthonormal sequence is complete if and only if, when all the coefficients are 0, x equals 0. And to give you an example of what this kind of theorem is saying, so you can kind of intuit what it's trying to say. Example, the sequence, let's do the sequence sine nx, so sine x, sine 2x, n going from 1 to infinity, is not complete. This is what we said last class. We said that it was not happy. The sine functions on their own are not happy. Now we know what not happy means. It means not complete. And the proof by theorem 3.4.14, all I have to do is I have to find a non-zero function that is inner product 0 against all the signs. And so you could say because cosine of x with sine of nx equals 0 for all n, but the cosine function is not the 0 function in L2. So in other words, the theorem says if the coefficients were the only function that has 0 as the inner product for every single thing in the sequence is the 0 function, and this is like how you use it in practice. You're like, I want to check if something is an orthogonal sequence or a complete orthonormal sequence. So I do the inner product against the sequence you gave me, and if it's always 0, it must be the 0 function. If that's true, it's complete. If there are functions out there that are perpendicular to everything in the list you gave me but are not the 0 function, then it is not complete. And so that's why it's an if and only if. Okay. So that's the kind of thing we're going to do. This is the kind of thing you would want. And the proof is going to use the last little theorem that we did that almost has like a little lemma. Is this statement kind of clear? The only thing that's perpendicular to your sequence is the zero vector. That's kind of what it's saying. Okay. Okay, so here's the proof. So there's two directions. Proof. This direction says if xn is complete, then for any x, for any x in H, we have x equals the infinite sum, n equals 1 to infinity of xn times xn. That's the definition of complete. So if you give me a list of coefficients, I reassemble the function x. That's what complete means. So by definition of complete. Complete. So what would happen if all the coefficients were 0? If xn equals 0 for all n, then we have x is equal to this infinite sum, like we just said, but the infinite sum is all zeros. And the only thing that you can get as the infinite sum of all zeros is 0, the 0 vector. Okay, so x is always, in a complete space, it's always equal to this infinite sum. And when all the coefficients are 0, you get 0. This is kind of the easy direction. If it's complete, then this 0 property will work out. The harder direction is the reverse. And this will remind you a little bit of the kind of thing you did on Tuesday with thinking of things that are perpendicular to everything. Okay, so this says, suppose x is such that xn equals 0 for all n. So we would like to show that x is actually the 0 vector. What do we know about x? We know that it's perpendicular to everything. And we know that it's a complete sequence. So here's what we're going to do. We're going to look at, is that what we want? No, I have the reverse. We just did that one. Okay, sorry. Yeah, suppose, let's get the direction here. Now I've bamboozled myself. Okay, we did this direction. If it's complete, then this property. And now we're doing the other property. So we're saying if the inner product is 0, that implies x equals 0. Okay, well, that's what we're doing. Okay, so suppose we know, let's rewrite the whole thing. I've confused myself. Okay, suppose we know and I'm going to write it like this. Xn equals 0 for all n implies x equals 0. Okay, so we have a machine. If you can check the inner product of a vector and check that it's 0 always, then you can conclude that the vector was the 0 vector. Okay, so we know that, and we want to show given any x in H, it must be that x equals the infinite sum of xn with xn. Okay, so in other words, this is the classic what we have and what we want. Have this, and we want this. Okay, fantastic. Okay, here's what we're going to do. Let x be given. Consider the infinite sum that we're interested in. Consider the infinite sum, the sum from n equals 1 to infinity of xn, xn. Okay, so x is some vector. We make this infinite sum. We don't yet know that this infinite sum equals x. That's what we'd like to prove. But we do know that it converges to something. By the Bessel inequality, this converges to something. We're in a Hilbert space. So since we are in a Hilbert space, that was the previous theorem. And since the infinite sum of the xn's is squared is less than the norm of x squared by Bessel's inequality, So by Bessel's inequality, the sum of these coefficients squared is finite. We're in a Hilbert space. So by the previous theorem, this converges to something. By the previous theorem, this converges to something. To something. Let's call that something y. Call it y. So y is equal by definition to this infinite sum. And that converges to, because the sum converges, this is some element of the Hilbert space H. Okay, this dot equals means by definition equal. We're defining y to be whatever this infinite sum is. This infinite sum we know converges because of Bessel's inequality and the fact that we're in a complete space, which is what we proved before. Okay, so what is our job? What do we have to prove? We have y. What are we trying to show? Yeah. Y is x. We want to show, so we've reduced what we want to show. This is all window dressing to show now that y equals x. We would like to show y equals x. If y equals x, then it must be that x equals this infinite sum, and then we're happy, we're done. What do we have? Okay, we haven't used what we have yet. Let's go back to what we have. We have a machine that says if you do the inner product of anything, then it must be the zero vector. Let's because x is already being used in our formulation. Let's rename that to z. Right? So this is like some kind of abstract machine that says if you can find the inner products of infinitely many things with the xn and they're all zero, then it must have been the zero vector. How are we going to use that to prove that y equals x? How could we possibly use what we have to prove that y equals x? What should we put in for z? Yeah. Exactly. Okay, so this is what we're going to do. We're going to let z equal x minus y. Let's compute the inner product of z with xn, also known as x minus y with xn. Okay, and we're going to compute this, and we're going to see that this thing is 0. And because it'll be 0, therefore by what we have, it must be that x minus y equals 0, and then x equals y. And we're done. So how are we going to compute this? So we're going to do the inner product. We're going to do the inner product of x minus y with xn. Okay? And x is just x, but y is an infinite sum. Oh dear. N equals 1 to infinity of x, xn. Okay, maybe let me do one step first. Let me split this up into two parts before I write the scary infinite sum minus the infinite sum n equals 1 to infinity of x, xn with xn. Okay, and now we're getting bamboozled by variables. So I'm going to rename xn to xk so I don't use n twice. Okay, I'm going to call this xk, and this is the sum from k equals 1 to infinity. Okay, so x minus y splits up. We got x with xn minus y with xn, but y is an infinite sum. And now we have an infinite sum inside of an inner product. Oh dear, what are we going to do? What can you do if there's an infinite sum inside your inner product? Is it okay to pull it out of the inner product? Yeah.
I think so.
Okay, why do you think so? Yeah.
Because we're in a Hilbert space, not just a normal inner product space.
It's true you need it to converge. If it converges to something, then it's okay to pull it out. So, and you're pointing out that this thing converges. There's an even more like practical, down-to-earth reason why you can do this. It involves where you were physically 2 days ago. Yeah.
It's just linearity of the first argument of an inner product.
It is eventually linearity of the first argument, but the real reason is we did this problem on Tuesday. This was problem 3, okay? So this was problem 3 on Tuesday's class. So this is by problem 3 on Tuesday. And it does boil down, so you need that this thing converges to something, and then you use linearity. You can take the finite sum and like approximate all this kind of stuff. By problem 3 on Tuesday. So inner products play nice with infinite sums. We can pull out this thing. Okay. So this is equals x, xn minus, and then I can move the infinite sum on the outside And that's all legit as long as the thing converges, which it does. Okay, so then I got x, got xk, and xn over here. Oh, yeah, okay. Let me pull it out one further. Okay, let me do it in 2 steps because I think that the steps are enlightening. Okay, we got x, xk, xk with xn like this. Okay, and I want to make them different colors so you can see what's changing and what's not. So the infinite sum pulls out. Now I have this inner product times xk, inner product with xn, and that's just a number. I can pull that out as well. So this is just a number. Okay, and then we're going to switch to just writing it the okay. And now this is one of those situations where things dramatically simplify. We have a big infinite sum, but this big infinite sum is actually quite easy to do. You should be able to tell me exactly what this infinite sum is equal to. What is the big infinite sum? Add up all infinity terms and tell me what is the total. Yeah? It's just xxn. And the reason is, as usual, xk with xn is, even though it's an infinite sum, is actually 0 in all but one situation. This thing equals 0 unless this thing equals 0 unless k equals n. So this big infinite sum is actually a sum of infinitely many zeros and exactly one non-zero term. And that non-zero term happens when k equals n. And so what you're left with is equal to xxn. And then you get the value of this thing when k equals n, which is xxn times 1. And xxn minus xxn equals 0. Whatever it is, we've subtracted it from itself. Okay, this is not super surprising. If you kind of like look at the big picture of what we've done, we made a vector y by doing the inner product of xxn as the coefficient. So the coefficient in xn was xxn. And then we said, please tell me the coefficient, right, by the coefficient extraction lemma. We said, what's the coefficient of xn in y? And it's not surprising it's xxn. Like, the way we constructed y and what we did over here are just undoing each other. So the coefficient in y of xn is xxn by the construction or by this calculation. The coefficient of x in xn is xxn. And so when you subtract them, you get 0. You get 0. X minus y, inner product with xn, is 0. This is true for every y, or for every n. This is true for every n. Leave a space and then do an exclamation point. Okay, and therefore, by what we have, the machine we have says if you have a vector whose inner product with xn is always 0, that vector must be the 0 vector. Therefore, x minus y is the 0 vector, and if x minus y is the 0 vector, therefore y equals x. Y equals x, and therefore x equals y, which is equal to the infinite sum that we wanted, as desired. Okay, beautiful little proof. Okay, questions or comments about this proof? So this reduces, if you want to check something is complete, all you've got to do is check that the only vector that has all 0 coefficients is the 0 vector. If there's any other vectors that have all 0 coefficients but are non-zero, then it's not complete. And in fact, you could chuck those in, right? You could keep adding things to your set until it's complete, right? You could hope that procedure would eventually work. Okay. Questions or comments? Okay, now I'm going to do the theorem that I gave a name for, this Parseval formula. Let me do Parseval's formula. Why are some of them theorems and some of them are formulas? I don't know. Theorem 3.4.15. It is Parseval's formula. And it says, if you have a complete sequence, so if the xn are complete, or is it an if and only if? Oh, it's an if and only if. Okay, so the xn are complete if and only if are a complete orthonormal sequence. If and only if for all x in the space H, the norm of x squared equals this infinite sum Okay. So you remember Bessel's inequality said that this is always less than this. Well, let's recall. Let's recall. Bessel says the norm of x squared is greater than or equal to this infinite sum always for any orthonormal sequence xn. And Parseval, this other dude, says the norm of x squared equals this infinite sum when complete. So Bessel's inequality is always true for any orthonormal sequence, and Parseval's formula just says, hey, it's an equal sign in that formula if and only if it's a complete sequence. So when it's a complete sequence, all of the size of x is accounted for by all the individual pieces that make it up. If it's an incomplete sequence and you're missing parts of it, then x will be larger than all the sum of all the parts that you have, because you've forgotten some pieces. If you were to add on the pieces you forgot, then you would get the difference. So it's an equal sign if and only if it's a complete thing. Okay, let's prove it. Prove. Okay, so proof, and we're going to do this direction. So if it's complete. Okay, by the way, this is in a Hilbert space. I said H, but let me say, let H be a Hilbert space. Let's add that, because we're going to use, again, this theorem. We're constantly using this theorem that says if you have these infinite sums, they converge to something, right? Let H be a Hilbert space. Okay. Okay. So by Bessel, we know that the difference x minus the sum of the first n of xk squared equals this difference. Right. So the Bessel's inequality, remember, we came from Bessel's equality, which was this thing. Okay. And what we are saying is now take the limit. Now take the limit. Now take the limit. So we have the limit as n goes to infinity of the difference, which takes a while to write down, is the limit as n goes to infinity of this side. And we're assuming that Parseval's equality holds. And when Parseval's equality holds, this limit is 0. This is comparing the norm of x to the infinite sum over here. So this thing equals the norm of x squared minus this limit. And that limit is exactly the infinite sum of the things. That's what an infinite sum means. And this is 0 by Parseval's formula, right? By Parseval's formula. So if Parseval's formula is true, then this thing is 0. Is this the other way that we're saying? We're saying if the formula is true. Okay, we're doing the, I wrote down the wrong direction. We're doing if the formula is true, then it's complete. Okay. So if this is 0, then this happens. Maybe were we doing both ways at once? What are we doing over here? Okay. Well, we're gonna use this equality multiple times. Why don't I split it up? Let's give this thing a name. Let's call it heart. Heart. Okay. And then so heart says the limit of the difference equals this thing. Okay. So now suppose this is the real proof of this direction. Suppose the norm of x squared equals this infinite sum, k equals 1 to infinity of xk squared, right? This is what people call Parseval's formula. So suppose Parseval's formula is true, i.e. Parseval's holds. then by heart, you must avoid the temptation to do a black heart, then by heart, the limit as n goes to infinity of x minus k equals 1 to n of xk with xk squared equals 0, right? Because in general, it's equal to this thing. And if this thing is 0, then that limit is 0. And what does it mean when this thing's 0? Well, that is exactly the definition of convergence, right? The partial sums are converging to x because their norms are getting closer to 0. And when the partial sums get closer to something, that's what we say is the infinite sum. Therefore, the sum k equals 1 to infinity of xk equals x by definition of convergence. Okay, and therefore, since this works for any k, or for any x, since this works for any x, the orthonormal sequence is complete. Okay, so that's if the formula holds, then this thing is getting closer to 0, and then therefore it's a complete sequence. Okay, what about the reverse? The reverse says if it's complete, then Parseval's theorem holds. How would that proof go? Suppose it's complete, then what? Yeah.
X equals the sum from k to
Yeah.
infinity.
Yeah, so in other words, if it's complete, then this thing equals that thing, so this limit is 0. So in this proof, we said, oh, the right-hand side is 0, and therefore the left-hand side does the thing we want. In the other proof, we say the left-hand side is 0, and therefore the right-hand side does what we want. So really it is kind of all coming from equation heart. Very good. Okay, so if xn are complete, let's say if they're a complete orthonormal sequence, then the left-hand side of heart equals 0. Equals 0. And again, this is the definition by definition of x equals the infinite sum, right? Right. So an infinite sum means the partial sums are converging to x, and the partial sums converging to x means the limit of the norm of the difference is going to 0, right? So exactly that thing is going to 0. And so therefore 0 equals the right-hand side of heart, which is this Parseval stuff. No, the thing squared. Therefore, Parseval's holds. Okay, so Parseval's formula is true, if and only if the thing converges. So basically, equation heart is relating the two things. Okay. Yeah.
Can you scroll up?
Yes. Of course. Okay. I think that is all we wanted to do for the technology of orthonormal sequences, and you can kind of see this stuff. These are very useful, and if you ever do like PDEs or like lots of applied things, these formulas are used all the time. This Parseval one saying that the norm of x equals the sum of the inner product squared. Sometimes you can interpret this as energy. So if you have like a wave, or you have like a string that's waving up and down, the norm squared of the shape of the string is equal to the amount of energy that is in the string. And so Parseval's theorem says the amount of energy in the string can be broken down into infinitely many pieces. It's the amount of energy in the first mode, where it's kind of going up and down with two things, plus the amount of energy in the second mode, plus the amount of energy in the third mode, and so on. So this has lots of interesting applications. If your string is moving, so it's not just has elastic energy, but it also has some velocity energy, then you have to use a norm that includes the derivative. This is called some other Hilbert space, not just L2. So this kind of thing is useful all the time. I remember I saw this stuff in like a third-year physics course before I took the math course, and they didn't explain why any of it was true. They're just like, look, it's true, like just do it. But now you know why. Maybe you haven't seen that course yet, in which case maybe it'll be more exciting when you do see that. Yeah, you can do the Leonardo DiCaprio meme when this comes up in your physics class on waves. Okay. Questions or comments before we move to chapter 3.5, which was the final the final section of the course we will do. Okay, let's move to section 3.5. So yeah, the textbook has a few other things, but section 3.5 is all about this idea of proving that the Fourier series are a complete orthonormal sequence for capital L2. So we want to prove that sines and cosines are complete. That is our goal. Okay, and here is the general strategy that we have. Where did I write this stuff down? Okay, here it is. So we're going to let phi n, we're going to enumerate the sines and cosines in order. So here's the general high-level outline. So let's call this step 0. Enumerate, that means put them in order. Enumerate sines plus cosines in some order. And we're going to call that phi. So we're going to do phi 0, phi 1, phi 2, phi 3, ... So you should think of, if you want, you can do like the 1 function. Okay, sines, cosines, and 1, and 1. So maybe phi 0 is 1, and then you could do like sine, cosine. You could alternate, however you want to do it. You add up all the sines and cosines, put them in some order, and call those things phi. And then we're going to define Fn to be the approximation with n pieces. So this will be the sum from k equals 0 to n of phi k. Okay, so the other way we were doing it is f phi k phi k. This is the partial sum that we've been doing this whole time. But instead of calling them xk, we're calling them phi. We're starting at 0 because we want to include the number 1 will be the 0th guy. And it's a function f in L2. So for f in L2. So this is our sort of notation that we're doing. Okay, we have this fn. So this is like our notation. What we want to show, we would like to show that fn converges to f in L2, right? And if it did, that is being complete, i.e. phi's are complete, right? Because what does it mean to be complete? It means that if you take the limit of the partial sums, you get back the original thing. That's quite hard to do. We have this theorem. That we just proved a minute ago. We have the theorem that says if we could show the only function f with fn equals 0 for all n is f equals 0, then we would have completeness. Then we would have what we want. So that was the theorem we did a minute ago. What number was that? Let's call it out by number. Bessel. Yeah, this one. Okay. It was theorem 3.4.14, right? If you have the inner products are always 0, then you get the 0 function. That's 3.4.14. By theorem 3.4.14. Okay, and notice actually we did a little upgrade. Fn is the approximation of the nth partial sum. And so the theorem says if all the inner products are 0. But if all the inner products are 0, then Fn is always 0. So if you do this nth level approximation, it's always 0. Then it would be that f is 0. And that would imply the thing that we want. Okay, however, it turns out even this is too hard. This is too hard to prove. Too hard to prove directly. So we're going to do a sneaky trick. And the trick is involving something called Cesaro averages. So here is the sneaky trick. And this is called the Cesaro average. We're going to define AN. AN stands for average. And it's the average of the first n f's. F0 plus F1 plus ... plus Fn divided by n plus 1. So there's n plus 1 of them. I'm going up to n, and I'm dividing by n plus 1. Some people call this the Cesaro. So Cesaro was some other dude. Cesaro average of f's. And let me give you a quick little example to tell you how these Cesaro averages work. Pretend f's were like this. f0 equals 0, f1 equals 1, f2 equals 0, f3 equals 1, f4 equals 0. So in other words, it goes 0, 1, 0, 1, 0, 1. In this situation, the limit of the f's does not exist. The limit as n goes to infinity of fn does not exist. So it's going 0, 1, 0, 1, 0, 1. The f's on their own don't exist. But if you do the an's, but the limit as n goes to infinity of the an's, well, the an is the average of the first n f's. f0 plus f1 plus dot 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 plus fn divided by n plus 1. What would that limit be in this case? Remember, the limit of the f's does not exist. So you can't just say the limit here is the limit of the f's, because the limit of the f's doesn't exist. What will it be in this case? Yeah. A half. It is a half. It's exactly a half. And that's because when you add up the top bit, okay, you have n things. It's either going to be n divided by 2 or it's going to be n divided by 2 plus 1 or something. And when you divide that by n, it's going to be converging to n over 2. So it's going to be like 1/2. So what is the point of this example? Is that Cesaro averages, they improve convergence. We started with a sequence that didn't necessarily converge, and the Cesaro average of it did converge. It's also true that if the limit exists, then the Cesaro average will be the same thing as the limit. Does anyone remember this problem from earlier in the course? Some people are nodding, yeah.
That was the first one on midterm.
This was problem 1 on midterm 1. So problem 1 on midterm 1 said, prove that if the limit of the f's exists, then the limit of the Cesaro average is equal to the same thing. That's what the midterm 1 problem did. And now we're going to use it. So the moral of the story is that the Cesaro average improves convergence. So even though it's quite difficult to prove that the f's converge, what we want is quite difficult to show that the f's converge to f. Proving that the Cesaro averages converge is easier. And so we will prove, we will prove if I can do it. So we will show the limit as n goes to infinity of f0 plus f1 plus dot 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 plus fn over n plus 1 equals f. So the Cesaro averages do converge. And this one is easier, again, because this is a more forgiving kind of thing to do. So this is doable. I will say, even though it's easier, I would guess this is like going to be the longest proof most people have ever seen. It's like a quite involved proof. But this is like the main thing we're going to do. It's a nice proof. I like it a lot. It's very, very sneaky. It involves double integrals. We're going to see when we get to it. Okay, so that's what we're going to do. We're going to start with this. Okay, does that prove what we originally wanted? We proved that the Cesaro averages converge to f. Does that prove the thing we want, which is that the f's on their own converge? Well, look at this example, right? If I prove the Cesaro averages converge to 1/2, does that prove the f's converge? No, they don't even converge. So why is this useful? Why are we wasting our time on the Cesaro averages? Why is that helpful? I'll let you see the whole board and then ask. Okay, well, I guess we got to do it like that. Well, why would it be useful to waste our time with these silly Cesaro averages? So the thing we want is all the way at the top. We described the strategy that said if the fn's are 0, then f has to be 0. That would imply what we want, right? We can prove this one. This one will be hard but doable. That says that the Cesaro average of the fn's is f. Is there some relationship between these things? Some way we can use them? Yeah. Yeah, that's right. So this one doesn't automatically prove the thing we want, but it proves this other thing. So in other words, there's a line. This property will prove this thing that I said was too hard. Okay? It's going to prove this thing. And then that one in turn will prove the thing we actually want. So it's like a 3-level thing. We're going to do this proof, which is a hard proof. This proof says no matter what the fn's are, this average converges back to f. If it was the case that all the fn's are 0, then the Cesaro average is also 0. You see? If all the fn's are 0, then what the limit on the left-hand side is 0. And because of this theorem, therefore f will have to be 0. And so that will prove the thing in green, the theorem we just proved. And then the thing in green will prove the other thing. So let's write this all down. This is like the high-level strategy of what we're doing. Okay, so here's our high-level proof. High-level proof that Fourier series converge using the thing in red, the fact that Cesaro averages converge. This thing. Let's give this thing a name. Dagger. Okay, dagger. Using dagger. Okay, so if you can prove dagger, that will imply what's going on. So how will we do it? Okay. Okay, so the proof. Okay, we will show the phi n's are complete. Phi n's are complete. It suffices to show that fn equals 0 for all n implies f equals 0. And that was the theorem, the name theorem from before. Theorem, what was it? 3.4.14. By theorem 3.4.14. Okay, so to show something is complete, it's enough to show that whenever the coefficients are all 0, the function must be 0. Okay. Now we say by dagger, if fn equals 0 for all n, then f is the limit of the Cesaro averages, f0 plus f1 plus dot 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 plus fn over n plus 1, which is the limit of all zeros. 0 plus 0 plus dot 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 plus 0 over n plus 1, and that limit is 0. There you go. And then we're done. So that's the high-level proof. It's connecting this Cesaro average thing and this trick of all the fn's being 0 implies the function is 0. That will imply completeness. And the conclusion is that actually not only is f equal to the Cesaro averages, f is equal to the actual limit. And so therefore f equals the limit of the fn's in L2, which is what we want to show. Okay, so that's going to be the proof. That's the high level. The thing that is going to take us basically one class is to prove this dagger, prove the Cesaro averages. Yeah. Questions or comments about this or any of this stuff? Okay, so we'll do, I think the way, yeah, things are great. We'll do the proof of dagger next Thursday on our last lecture. On Tuesday, we'll have more practice with these things with convergence and completeness and stuff like that. I think we have enough material that there won't be a video. So it'll just be on this stuff with Bessel's inequality and inequality and Parsevals and like practicing doing like inner products and sums and stuff like that. Okay, any questions or comments? Okay, I'll be around for a while if you wanna chat. Otherwise, we'll see you on Tuesday. If you might want to review some of this stuff, make sure it's making sense to you for Tuesday's problems.